Hello guys, thank you so much for being with me in another machine learning tutorial video. Continuing the discussion of unsupervised learning, we come to the discussion of anomaly detection. There are different names for this discussion, such as anomaly detection, outlier detection, or density estimation, or two-class classification. We have some data. This is a real data related to computer network. The horizontal axis is related to delay and the vertical axis is related to efficiency. Each of these data is an observation, and the blue data is our normal data. Some of these data are very outliers and are far from normal data. These observations are called anomaly. The goal is to introduce an algorithm that can detect these anomalies for a set of data. For this reason, you may mistakenly assume that this is a two-class problem, classification problem, I mean. Whereas at the beginning, we did not have one more type of data, and it is different from classification problems. A good example of these issues is fraud detection in bank transactions. If one of the bank transactions of a user is very different from the user's usual transactions, the system recognizes that this data is outlier. Another example is in the security of a computer network. The system can detect the abnormal user activity, so we are actually dealing with probability. Because in these issues we are looking for observations that are very unlikely to occur. Therefore, we have a probabilistic approach. In the first step, we try to fit a normal distribution on these data. We all know that every probability distribution has a mean and a variance. It is enough to get these parameters for the data. In this figure, I have fitted a Gaussian normal distribution. As you can see, we have displayed this distribution with some contours. The data located in each contour has a certain probability of occurrence. Closer the contours are to the center, the more likely the data is to occur within them. We are looking for improbable data in these issues, and we choose a threshold to detect this data. For example, the data that are inside the central contour their probability of occurrence is higher than the others. All data outside this contour and inside the next contour have probability of occurrence. Therefore, we consider this contour as a threshold. That is, the data that are outside the contour are called outlier data. The distribution that we usually use is in anomaly detection problems is the Gaussian distribution. Try to read about it if you don't know enough about it. We also explain a little here. We start with one-dimensional and one variable normal distribution, and then we see its effect by increasing the dimensions. This distribution is defined by two parameters, the mean known as the mean and the dispersion known as the sigma. In this distribution, the probability of data occurrence is a maximum in the center, and the probability of data occurrence decreases as you move away from the center. The severity of the reduction of this probability is determined by the sigma parameter. You are definitely familiar with the relationship of this distribution. This distribution is a continuous function and is the most widely used type of probability distribution. For now, we are talking about the univariate distribution. A special case of normal distribution in which the center and the mean are 0 and the standard deviation is 1, which is called standard normal distribution. The lower the standard deviation, the steeper the slope of the graph. Normally, more than 99% of the data are between the mean minus 3 times the standard deviation and the mean plus 3 times the standard deviation. This is the role of the dispersion and standard deviation parameter. How far the data is from the center. With the mu parameter, we can determine the center. So the problem is that we have a set of unlabeled data. We have observations in one-dimensional space. The goal is to fit a normal distribution on this data. It is enough to be able to estimate the mean and standard deviation from this data. Obtaining these parameters is very simple. Actually, this formula is related to sample mean. After obtaining the average, the mean, we can obtain the standard deviation or dispersion. It means to estimate how far the data is from the average. Now we have the normal distribution, and now we need to set an epsilon as a threshold. Here we need to take help from the MLE technique. We want to determine the parameter in such a way that the product of data occurrence probabilities is maximized. We said that instead of maximizing the function itself, we can increase the logarithm of the function. Because the logarithm is a strictly ascending function, the likelihood function contains the same parameters. Only one logarithm has been added to it, so just maximize the logarithm of the probabilities or minimize their negativity. So we found the cost function. So the algorithm in general is a simple algorithm. Our inputs in the training set are each a vector. In the n-dimensional space, we state two assumptions. That may not always be the case. For now, we assume that both are true. The first assumption is that we assume that our data follows a normal distribution. If we map the data onto the x1 axis, the x1 feature, then they do indeed follow a normal distribution. Likewise for x2. That is, we assume that each feature follows a normal distribution, and if the contour axis of the distributions do not have an angle with the coordinate axis and are parallel, then we say that the function is not correlated. If these axes have an angle with the coordinate axis, it means that the features are correlated. Here we assume that the features are independent and uncorrelated. That is, the covariance matrix is diagonal matrix. In the real world, data usually follows a normal distribution, but if this is not the case, we use other distribution. Or we can use a series of preprocessing and then make the data follow a normal distribution. So we calculate a center and the dispersion for each feature. Because we have assumed that the features are independent of each other, so the probability of both occurrences is equal to the product of the probability of each. This is a simplifying assumption. We cannot always consider this assumption, and this second assumption makes us need fewer parameters. That is, we only need to estimate two parameters, mu and sigma, for each feature. The more parameters we need to estimate, the more data we need. This assumption only makes our work easier, and later we can eliminate the assumption. The first important thing to do is what information and features can be useful in anomaly detection. In the example of a bank user and the detection of strange and different transactions among transactions, the important features are the number of daily transactions of a user, the amount of each transaction, the average amount of transactions, and something like this. Or in the computer network, these features include the bandwidth consumed by each user, the ports associated with the user, and many other features. In the discussion of anomaly detection, determining the characteristics is a very important task. In the next step, we need to estimate the parameters. The next step is to calculate the probabilities. Here we plot the data on the x1 axis. Now we calculate the mean and dispersion. We do the same for x2. All these implementations are available in the Python files, so please pay attention to them. So each feature has a univariate normal distribution. The product of these two normal distribution is the contour shape which is available in the Python files. You can see that the dispersion is also different in x1 and x2. You can see in this contour figure 2. The dispersion is also different in x1 and x2 direction. This means that these ellipses are more elongated in the x1 direction. Almost all data falls within the third contour. Let's assume that epsilon is 200 here. Now, since this is 0.04, more than this threshold, then this data is normal data. Now we test another point because 21/10,000 is less than 0.02, then this data is an outlier. You can see these examples in the Python files. This issue is very simple and easy to code. If we have a numerical criterion, we can understand whether we have chosen a suitable feature or not. For example, accuracy is a numerical measure, but it cannot be used here because in such problems, most of the data are normal data and there are very few outliers. That is, if we consider these problems as two-class classification problems, one class has 300 members and one class has 5 members. In cases where the data is unbalanced, that is, many of them are normal and a few of them are abnormal, we need other criteria. As usual, we divide the data into 3 categories: training data, validation data, which are few in number, and we have labels for each. Another group of data is the test data. What's important here is that the training set only contains a X and does not have a Y label. Suppose our training set is related to the performance of engines. For example, an engine company has produced 10,000 healthy engines and 20 defective engines. We have to divide this data again into 3 categories. For example, we choose 6,000 healthy engines from normal data. As training data, we set aside half of the remaining 4,000 healthy engines for validation and half for testing. In this example, we have 2010 data and only 20 engines are faulty. Such examples are called single class classification problems. The algorithm used to solve these examples is a type of SVM algorithm. When we split the data, now we calculate a normal distribution for each data and feature. Multiplying these probabilities, we choose a threshold. If we encounter new data based on this threshold, we check whether it is healthy or defective. Now there are some criteria to evaluate this algorithm. Among these, our goal is the F1 score. Another application can be to use this as F1 on validation data to find the best epsilon. Y is equal to 1 means the data is normal, and y is equal to 0 means the data is outlier. So these four situations may occur. False if we detect that a data is an outlier but is actually normal. If we recognize that a data is normal and it is really normal, it is true positive. If we detect that a data is an outlier but is actually normal, this is false negative. And if we determine that a data is an outlier and it is really an outlier, it is true negative. If we recognize that a data is normal but is really an outlier, it is false positive. This matrix is also called confusion matrix. There is no need to memorize the matrix, you just need to know the logic. And now we will define two criteria based on this. Precision measure, recall criterion. Note that there are times when you have to go to these metrics when you have a lot of normal data and a lot of abnormal data. We have a set of positive predicted data which is equal to the sum of correctly predicted positive data plus false positive predicted data. Precision is the fraction of data that are positively predicted correctly. Recall is the fraction of positive data that are correctly recognized. This may seem a little confusing at first, but once you understand the concept, it's really not that complicated. Each of these is in the range of 0 to 1. Because these four concepts are non-negative, we like these metrics to be as close to 1 as possible. The ideal situation is that both approach 1 at the same time, but sometimes it is not possible. Increasing precision will decrease recall and vice versa. In some cases, we have to prioritize ourselves. Sometimes we cannot choose one over the other. In these cases, we use the F1 criterion, F1 score. The maximum criterion is the value of 1. Its minimum value is very close to 0. We like to maximize F1. By maximizing F1, we have actually maximized the two other criteria. Let's have a comparison between the two categories of supervised learning with anomaly detection. And the first point is the ratio of the number of positive to negative samples, where positive means data outliers. Another characteristic, the anomaly itself may have different types into classification problems. Positive examples are very similar, but in anomaly detection problems, each outlier may be completely different from the other, and each can really be considered a class. Again, I have given you some examples. For example, the ratio of data in spam or non-spam emails is not very different. Regarding feature selection, we have said that we assume that the data follows a normal distribution, but in some cases it is not. Here we have generated 10,000 data, but most of them are located at the beginning of the domain. In fact, these data follow the gamma distribution. There are different ways to convert to normal distribution. One of these ways is to reduce this data to a number smaller than 1 and try this with several numbers and draw the corresponding graphs. We compare which one is closer to the normal distribution. But the other point is what are the characteristics themselves. We want to compute features such that the value of px is very large for normal data and small for abnormal data. For example, here we consider the green data as probably normal. Now, why do we recognize so easily? Because the problem has become two-dimensional. If you consider the original problem, you can see that the feature probability x1 is not very expressive and they cannot distinguish between normal and abnormal data. This is due to the same correlation of features. We like to choose features so that if the data is an outlier, it will be far away. We ourselves consider the features to be independent, but it may not be true. Usually, the longer the delay, the lower the efficiency. I mean, in computer network issues. That is, there is a negative correlation between the features. What we can do here is somehow combine these features. For example, multiply or divide them together. In this way, we have considered this correlation in a way. For example, processors have a direct correlation with network traffic. If we consider this separately, in the end, the model we make will not be a very good model. Here we have two features that clearly have a positive correlation between these two features. Here, if we obtain the normal distribution for these features separately, the problem that will be obtained in the end will be like this. This green data is abnormal data. Given this distribution, this data would be classified as normal, which is wrong because when the processor load is low, high memory consumption has been observed. For example, a processor may be stuck in an infinite loop. If we use the separate normal distribution, this problem would not be identified. A better way is to fit a bivariate normal distribution. To explain this function, you need to be familiar with the multivariate normal distribution relationship. I suggest that if you are interested, read more about it, although it will not be very useful in coding, and just knowing about this relationship is enough actually. Okay, I did not want to bore you, and I will transfer the rest of the concepts to the next video, and of course there are slides here available for you. I again highly recommend you not to miss neither the Python files nor the upcoming lectures, since inside both of them there are very practical and important tips for you. Have a nice time.